All right, today we're going to pull back the curtain on one of the most critical topics in all of technology. How do you design a system that doesn't just work, but can actually survive massive, overwhelming success? We're talking about the architecture of scale.
So picture this. You did it. You poured months, maybe even years into building this amazing application. You finally launched it. It's out there, in the world. It's live. And you know what? It's working perfectly for your first handful of users.
And then, bam, the moment every creator dreams of. Some huge influencer finds your app and tweets a link. And that user counter just starts spinning like crazy. 10 users, 100, 10,000, and then all of a sudden, 1 million people are rushing to your site all at once.
And just as you're about to pop the champagne, it all goes red. The site is down. Your server is basically just caught on fire. Your app is dead. The very success you were hoping for is the exact thing that just destroyed your entire system.
This is a classic scenario that we call the success disaster. It highlights one of the hardest lessons in software engineering. I mean, building a feature is one thing, but architecting a system that can actually survive the chaos of the real world, well, that is a completely different ballgame.
So how in the world do we prepare for this? The answer is something called system design. And listen, this isn't about writing more code. It's about taking a huge step back and drawing the blueprint. It's the high-level plan for how all the different pieces are going to fit together to handle those moments when 1 million people click buy at the exact same time.
Okay, so your single server is completely choking under the load. You need more power, and you need it like yesterday. This brings you to your very first critical decision, and it really comes down to 2 fundamental choices for scaling.
On one side, you've got vertical scaling, or scaling up. Now, this is the easy path. You just buy a bigger, faster, more expensive computer. More RAM, faster CPU, the whole deal. The problem? Well, there's a hard limit. Eventually, you just can't buy a bigger machine. On the other side, you've got horizontal scaling, or scaling out. So instead of one giant supercomputer, you buy 10 or maybe 100 cheap ones and link them all together. This is basically limitless, but it introduces a brand new problem: total chaos.
So, you've decided to scale out with a whole bunch of servers. That's awesome for handling traffic, but yeah, it creates a whole new kind of chaos. How do you direct all those incoming user requests to the right server without everything getting lost?
And this brings up a huge question, right? You've got 10 servers ready to go, and 1 million users are trying to connect. How does a user's phone in, say, another country know which specific server to talk to? The simple answer is, well, it doesn't. It has no idea.
And this is where we introduce our hero, the load balancer. You can literally think of it as the digital traffic cop for your application. It sits right in front of all your servers and becomes the single point of contact, intelligently directing the flow of all that incoming traffic. So here's how it works in practice. A request arrives at the load balancer. The load balancer takes a quick look at the health of your servers. It sees, okay, server 1 is busy, but hey, server 2 is totally free. So boom, it routes the request to server 2. If server 3 completely crashes, the load balancer just stops sending any traffic there. It's the absolute backbone of a horizontally scaled system.
Okay, so our server problem is solved. We can handle millions of connections now. But what often happens is when you fix one bottleneck, you just reveal the next one down the line. And that next one? It is almost always your database. So, why is the database the new choke point? Well, because most databases read information from a physical, spinning hard drive, which, in computer terms, is just incredibly slow. Now imagine 100,000 people are all asking for the top 10 trending videos at the exact same time. Making your database answer that same slow question 100,000 times will bring it to its knees, for sure.
The solution here is a really elegant speed hack known as a cache. A cache is just a super high-speed data storage layer. It uses a computer's RAM, its memory, which is lightning fast, to store a small amount of your data, specifically the data that gets requested over and over and over again.
Let's just walk through it real quick. The very first user requests the trending videos. Okay, we go to the slow database one time to get the answer. But then, and this is the key, we take that answer and we store it in the lightning-fast cache. Now, the next 99,999 users who ask for the same thing, they get the answer instantly from the cache, without ever bothering the database again. It's a total game changer for performance.
We are in really good shape, but there's one last major hurdle. What if your users aren't just reading data? What if they're actively creating it? You know, uploading photos, posting comments, liking posts. You can't really cache that kind of dynamic activity.
So guess what? The database is, once again, the bottleneck. So to solve this, we need a really key insight about how people actually use the internet. It turns out that for most apps, the vast majority of traffic, we're talking like 80%, is just people reading data, like scrolling through a feed. Only a tiny fraction, maybe 20%, is people writing new data. And this imbalance, it allows for a very, very clever solution.
And that solution is called database replication. The strategy is pretty much what it sounds like. We divide and conquer our database work. We create one single master database that handles all of the write operations. And then that master automatically copies the data over to a bunch of read replicas.
So here's how the data flows. Anytime a user creates a new post or leaves a comment, that write request goes to one place and one place only, the master database. The master then immediately copies this new data to all of the read replicas. So now, that huge volume of read requests, that 80% of your traffic, can be spread out across all those replica databases. This keeps your supercritical master database protected and totally free from overload.
So look, we've covered a ton of ground here, piecing together the core components that let an application scale from just one user to millions. But now we get to the real secret of system design.
These 4 concepts right here: horizontal scaling, load balancers, caches, and database replication. I mean, this is the foundation. If you truly understand these 4 ideas, you understand the basic principles that keep giants like Netflix, Amazon, and Google online every single day.
But here it is, the secret that really separates experienced engineers from everybody else. There is no such thing as a perfect architecture. It doesn't exist. There's no single right answer. There are only trade-offs.
So what does that actually mean? It means you're constantly playing a balancing act. For instance, you might decide to trade higher costs for way better performance. Or maybe you accept more complexity in your system in exchange for it being more reliable. A senior engineer's real job isn't to know every fancy tech buzzword. It's to understand which trade-off is the right one to make for the business right now.
So you've done it. You've built a system that is scaled, balanced, cached, and replicated. It's ready for that million-user stampede. But you know what? The work is never actually over. So the real question is, what trade-off are you going to make first?